Hi guys, so in this video I'm going to be talking about the collision of particles and the intersection of lines. And I just want to make sure that we distinguish between the collision of a particle and what the intersection of a line is. A particle may travel along a line, but it only exists on that line at one point at one time. Whereas an intersection of a line, we're just looking for where two lines intersect each other at a point. So the main difference is for two particles to collide, they must intersect at the same point, obviously, but that the extra condition is that they must pass that point at the same time. Otherwise, they won't collide each other. They'll pass the same point, but if they don't pass at the same time as well, they won't actually collide with each other. Now, because of this, it is useful to write the vector equations with the same parameter. So we've been using lambda so far. Usually when we talk about collision of particles, we'll do it with respect to time, for obvious reasons. But it's not necessary to have the same parameter for both of the particles. And we'll go through an example at the end like that. That's different for two lines. So if for two lines to intersect, they must intersect at a point, but possibly for different values of parameters. And we'll go through an example of what I mean by that there. Thus, when you're writing the vector equations of two lines, we usually use different parameters. So we won't choose the same parameter. We do use different parameters when we're writing the vector equations of a line. But when you're writing the vector equations of a particle, we try to write them with the same parameter. But it's not necessary. You can write them with different ones. Let's just go over a few basics quickly. I'm going to look at lines first. Intersection between two lines. So we obviously have a 2D case and we'll have a 3D case later on. But obviously the two lines will intersect as long as the lines are not parallel to each other. And as you can see there, line 1 and line 3 are parallel to each other, assumedly, and they won't cross over. However, line 2 isn't parallel to line 1 or line 3, so it intersects both lines. So the principles apply, just like with normal lines. But when we're looking at vectors, we're looking at the direction vector because that is what the direction of the line is. So as long as the direction vector of the first line isn't a scalar multiple of the second line, they will intersect each other, because if they are scalar multiples of each other, then they are parallel lines. So for example, I always do the mx plus c cases first, and then I'll relate that to the vector equation second. So if I pick this line here, y equals 4 over 2x plus 8, and if I've got y equals 2x plus 3, these two lines are actually parallel to each other because 4 divided by 2 is 2. These two lines will never intersect each other because they're parallel. Likewise, if I have a direction vector, so I'm calling B the direction vector of my lines now. So if the direction vector of the first line is AB, and if the direction of the second line, B2, is the scalar multiple, I'm calling this mu, mu, that's how I'm pronouncing it anyway. The scalar multiple mu times this vector here, that means that B1 and B2 are actually parallel lines. So if one direction vector is a scalar multiple of another one, like we've got over here, B2 is a scalar multiple of B1, then those two lines will be parallel because they're going in the same direction. So here's a quick example. If I have a direction vector 4, 2, and 3, if I have a direction vector minus 8, minus 4, and minus 6, these two are actually parallel lines if these are the direction vectors of those lines. And why is that? Because this minus 8, minus 4, minus 6 is actually a scalar multiple. So the 2 is the scalar multiple, and we're timesing it by the first vector there. So because the second vector is a scalar multiple of the first vector, those two lines are parallel and they won't actually intersect. That's the first thing I'll check if I'm seeing if two lines will intersect or not. Are their direction vectors parallel or not? Because if they're parallel, they won't intersect. The next case we can look at is the 3D case. 3D cases are similar to 2D cases, but there's a new word called skewness. So in a 3D case, the lines can be parallel and not intersect. That's something that could happen. The lines could be skew and not intersect. Now, the definition of skewness is that the lines are not parallel, and they do not intersect. That is the definition of two skew lines. They are not parallel and they do not intersect. And obviously the third case could be that the lines will intersect each other. So they're not skew and they're not parallel, so they will intersect each other. All the lines, this is how I generally write the equation of lines. Again, I'm distinguishing lines from particles. If I have a line 1, I'm just calling this R1 here. This is the equation of the first line. This is the vector equation of the second line. And you can see that I have actually used a different parameter for each one. For the first line, I'm using the parameter lambda. And for the second line, I'm using the parameter mu. Now, for these lines to intersect, there must exist a lambda mu over the real numbers. So there must be a lambda mu value such that the equation of the first line will equal the equation of the second line, or a lambda mu combination. And again, lambda doesn't necessarily have to equal mu, because we don't want them to happen at the same time. We don't care. We just want them to be able to cross each other. If this was a particle situation, then I would want lambda to equal mu as well for the particles to collide. But right now we're just talking about lines, so as long as we have a point that they cross over, I don't care if these two are the same or not. As long as there is a lambda mu combination that makes this true, then the two lines will intersect each other. Let's look at an example now. It says find the point of intersection between the lines L1, so they've given us the vector equation of L1, and L2, they've given us the vector equation of L2. I'm not a fan of component form. I always like to write mine in vector form. So I'm going to write R1 equals, and I'm just going to call this, let's call it RA. That's line A, and we'll call this line B. RA is going to be 17 plus lambda times 7 negative 2. And we'll do the same for B. So the vector equation of the second line, 16, 3 plus mu, that's a different scalar multiple of 3 and 2. And we want to know, do these two lines intersect? It says find the point of intersection. So that's kind of a hint that they will intersect each other. Now, on the previous page, what I said was, for these two lines to intersect, we need the line A to equal the line B at some value of lambda and mu. So what we end up with is we want a 7 plus 7 lambda and a 17 take away 2 lambda be the same as 16 plus 3 mu and 3 plus 2 mu. And what we can do now is we can just make sure that our x components are the same, because obviously for them to intersect, the x components have to be the same and the y components have to be the same as well. So let's look at the x components first. So I've got 7 plus 7 lambda equaling 16 plus 3 mu. And then we've got this equation here of 17 take away 2 lambda equals 3 plus 2 mu. To solve this algebraically, what I'll have to do is I'll have to write everything in terms of lambda or everything in terms of mu and then solve for that variable. Or what I could do is I could use the elimination method, which is what I think I'll do here. So this is my first equation. This is my second equation. And I think I'll use the elimination of variables method to solve these two equations simultaneously, because it's two equations, two unknowns. So what I've got is 7 plus 7 lambda equals 16 plus 3 mu. And on the second line, I've got 17 take away 2 lambda equals 3 plus 2 mu. Now, the 3 and the 2 look like the nicer combination. And I know that if I multiply the whole top line by 2, I can multiply the whole bottom line by 3. This will set up the new equation to allow me to eliminate these two variables. So timesing everything by 2, I've got 14 plus 14 lambda equals 32 plus 6 mu. And then I've also got 3 times 17, 30, and 21. So that's going to be 51. Take away 6 lambda equals 9 plus 6 mu. And obviously I'm going to do the top line, subtract the bottom line, or vice versa, it doesn't make a difference. So 14 take away 51 is going to give me 36, 37. 14 take away -6 is going to be plus 20 lambda. 32 take away the 9 there. Give me 22. 23 actually. And 6 take away 6 gives me 0 there, which is what I want. And then I have 20 lambda equals, and 23 and 37 is going to be 60. So lambda is going to equal 3. Then how do we find the mu? We can substitute it into any one of the equations here to find the mu value. I'm going to pick the second equation there. So 17 take away 2 times lambda was 3 equals 3 plus 2 times mu. So 17 take away 6 is 11. 3 plus 2 mu. Take that away. 8 is 2 mu. Mu is 4. So these 2 points do intersect. They intersect when lambda is 3 and mu is 4. But it wants us to find the point of intersection. So all I have to do now is substitute that into either RA or RB. And then we'll decide whether we're going to use mu or lambda. So let's just work through that one quickly. If we do RA given lambda is 3, what we end up with is 17 plus 3 lots of 7 is 21, 3 lots of negative is -6, and this gives me a point 28, 17 take away 6, 7. And then let's see, we shouldn't actually have to substitute into the second equation, but let's do it just to make sure that we did it right. So the position vector of B, given that mu equals 4, now mu is 16 and 3, and the mu is 4, so 4 times 12 is 8, 16 and 12 is 28, 3 and 8 is 11. Now you can see that when we substituted in the lambda and the mu, we did get the same point of intersection for the first line and the second line there. So there was a point of intersection between L1 and L2. It happened when lambda was 3 and mu was 4. And the point of intersection was 28 and 11. So you'd actually have to write that. Therefore, the point of intersection is 28 on the x-axis and 11. Then that's it. Let's just quickly look at 2 ways to do this on the class pad. So the first way is if you don't have any activities, we can use main. Just go clear all the variables as well. Now what you're gonna have to do is you're gonna have to set up these 2 equations yourself first. So that's the work that you will have to do. Then what we're going to do is we're just going to set up 2 equations here. Now where I see lambda, I'm just going to use x, and where I see mu, I'm just going to use y, because it's just convenient on the actual class pad itself rather than going through the ABCs and putting lambdas and mu's and stuff in there if you wanted to do it that way there. Under a time pressure and exam, you don't want to be doing that. So x, y, and z, we could have used x, y, and z there. It doesn't make a difference. So 7 plus 7x equals 16 plus 3y. Again, x is my lambda, y is my mu. And then 17 take away 2x is going to equal 3 plus 2y, 3 plus 2y. And we're solving for xy. And if I've done everything correct, what I should get is my lambda value is going to be 3, and my y value is going to be 4, which is my there. Yeah, x is 3, y is 4. And then what you could do is just substitute that 3 back into the first equation there to get your coordinates or your point of intersection. Alright, let's move on to the next question. Now, this question here is going to involve 3 coordinates. And so it's a little bit trickier, but we can make it work for us. And again, we're just going to follow the same principle. So find the point of intersection between this line and this line here. Now I'm going to call this line A, and I'm going to call this line B. That should be line 2 there as well. Okay, so that's line A, that's line B, and we're going to find the intersection between line A and line B. Again, what I'm going to do is we're going to set it up saying that RA equals RB, and then we're going to write this as a single term here. So that's just going to be lambda 1 plus 2 lambda, and then 2 plus 3 lambda. 2 plus 3 lambda there. And that's got to equal this equation over here, which is 3 take 4 mu, 2 take 3 mu, and then 1 plus 2 mu. 1 plus 2 mu. And again, we need the x, y's, and z's to all cross for the exact same value of lambdas and the exact same value of mu's. But the lambdas don't necessarily have to equal the mu's. So again, we're just going to equate the x terms. So lambda equals 3 take away 4 mu. We'll just go down here. The second equation there is going to be 1 plus 2 lambda equals 2 take away 3 mu. And the third equation for the z component is going to be 2 plus 3 lambda equals 1 plus 2 mu. Now this equation here is quite nice because we've got lambda equals 3 take 4 mu. So I can just substitute that into the y equation over here. So 1 plus, and then 2 lambdas will be 6 take away 8 mu. 2 take 3 mu. And we'll do the same for the z components here. So 2 plus, and now we're on 3 lambdas. So that's 9 take away 12 mu equals 1 plus 2 mu. Now let's solve for mu. And if all the mu's are the same, we should end up with the two lines intersecting each other. So let's solve the y components first. So I'll bring these 8 mu's across to this side, which leaves me with 5 mu's. 1 plus 6 is 7. 7 take away 2 is 5. So here we've got mu equals 1. Let's solve this side now. We'll bring these mu's across, so we'll have 14 mu's. 2 plus 9 is 11. 11 take away 1 is 10. So this mu is 1.4. Now notice that I said before that all the mu's have to be the same. All the lambdas have to be the same. At the moment we've got 2 mu's that are different. Okay, so for these two lines to be the same, we need the first mu to be 1 and the second mu to be 1.4. Unfortunately, they can't do that at the same time. So since the mu equals 1 up there doesn't equal that mu equals 1.4, because they're different, what we have is that the line RA does not intersect the line RB. So before, we only had two equations, and we found that the lambda values were the same, the mu values were the same. When we put those lambda mu values into line A and line B respectively, we got the same point out. If we did the same for this example, if I put lambda equals 1 into here, what you'll have is that these two will not line up properly, because there's a disparity between the y values and the z values now. So these two lines will not cross. So what else do we know? We know that these two lines are not parallel, because there's no way, that's the direction of the first line, there's no value, there's no scalar c that will make this true. There's no possible way to get from there to there by multiplying this by a scalar or by multiplying that by a scalar. These two lines are not parallel. Because they don't intersect, we can say that the lines RA and RB are skew. Because remember from before, the definition of skewness is that the lines aren't parallel and they don't intersect. In this case, the two lines do not intersect. Let's just move forward now to the talking about a bit of particles. It's very similar to solving the equations of two lines, but again, there's that extra restriction that they have to collide at the same time as well. So not only do their lines have to cross, but they have to cross at the same time. So I'm just going to go through an example quickly. At time t bigger than or equal to 0, the position of 3 ships is given by this vector, and this vector. And I've written all these vectors in terms of a t value. Okay, so I'm going to assume that they all leave their respective initial positions This is the initial position. This will be the initial position for the second ship. This is the initial position third ship. This is the direction of the first ship, direction of the second ship, direction of the third ship. And I'm assuming that they're all leaving their initial positions at the same time. And the question is to determine if ship A and ship B will collide. Alright, so what do we want? We want to find out where the position vector of A is the same as the position vector of B. Now the position vector of A is going to be 186 plus 8t and 44 plus 12t. So that's just the x and the y coordinates respectively. We want those to be the same on B. So 228 take away 16 B and 58 plus 40. Alright, and again, what we need to do is we need to make sure that the x values are the same at the same time, and the y values are the same at the same time, but the time must be the same between x and y. That's the important bit. The x and the y bits need to be the same, and they must cross at the same time as well. So what we're going to do is we're going to compare the x ones first. So we want 186 plus 8t be the same as 228 take away 16t. Now we'll bring the 16 across, and that's going to become 24t equals, and 228 take away 186 is, work that out now, 228 take away 186, big easy numbers. That's going to give us 42, and when we divide 42 by 24, we get 1.75. So time 1.75, the x coordinates are the same between the two ships. Now we need to make sure that that's the same for the y coordinates. So 44 plus 12t equal 58 plus 4t. Bring the t across, we're going to have 8t equals, now 58 take away 44 is 14, and again 14 divided by 8 is 1.75. So we can see that at time 1.75 the x and the y coordinates are the same, they cross the same point at the same time. Now we just need to determine what that point is. How do we do that? We can substitute the time into any one of the two equations there. So I'm just going to substitute it into the point A there. So we want 186 plus 8 times 1.75. And we want 44 plus 12 times 1.75. And when we do that, we're going to get 186 plus 8 times 1.75, which is 200. At the position 200 in x values, and we're going to do 44 plus 12 times 1.75, and we're going to get 65 there. Now, how could we have solved this a lot quicker on the calculator? Again, we could have just used solved in the class pad with the simultaneous equations. What I want to do now is I want to go through the same example, but I'm going to go through it if we chose different values for t, these two t values here. Because sometimes they can actually make the problem easier and give us more information if we choose different parameters when we're talking about collisions of two particles. Alright, so this time what I'm going to do is I'm still going to write this. It's still the same problem. Okay, so we're still trying to solve where r at A is the same as r at B. This time I'm going to call this one T1, and I'm going to call this one here T2. I'm going to say that there are different time periods. So 186 plus 8t1 and 44 plus 12t2. That's like two new variables now, or parameters I should say. And we'll do the same thing. It's t1 still. We're multiplying it all by t1. Yeah, we've got 228 take 16 t2 and 58 plus 4 t2. And again, we want the x coordinates and the y coordinates to be the same at the same time. So here we also need to check that t1 equals t2. So that's the additional check there. Alright, so we'll do the same thing. We'll do 186 plus 8t1 equals 228 take away 16t2. And we've got 44 plus 12t1 equals 58 plus 4 t2. And then we can solve these again simultaneously. I'm not going to go through that process. I'm just going to use the class pad quickly. So if we set it up in the class pad, I'm going to have 186 plus 8. I'm going to call t1x. I'm just going to call t1x, and that's got to equal 228. Take away 16y, and we want to make sure that we've got 44 plus 12x equaling 58 plus 4y, and we're solving it for x and y. And lo and behold, the t1 and t2 are the same. Okay, so again, we're going to have t1 equaling t2 equaling 1.75, which is the exact same result as we had before, t2 equaling 1.75. Then we'll go through the same process again to find the point of intersection, which is 265. Let's just look quickly at a visual representation of what's happening. What we had was ship 1. Okay, so ship 1 started out here, and ship 1 was traveling in a particular direction. So we're traveling along this line here. So that was the vector equation of the line. Obviously t is greater than or equal to 0, so it can't actually go this way here. So when ship 1 is moving, what we've got is lambda there is just the value at time t. You can see it's traveling up here. And what we want to know is does it collide with ship 2? Now, ship 2 is traveling along this line. As you guys can see, the two lines intersect, okay? And that was the first thing I was talking about before. The lines might intersect, but the question is, does ship 1 and ship 2 cross this point at the exact same time? Because if they don't cross at the same time, they're not going to collide. So when we go out a bit here, let's just move forward in time. So this is a time 0. As we move forward, we can see the two ships coming together. And you can see that they actually come together when x is 200 and y is 65, which is over there. Even if we zoom in, we can still see that at time 1.75, it only goes up in 0.1s here, but they will collide with each other. The two lines are colliding with each other over there. And I'll just let that play out a little bit. So if we just let the slider play out, this is what happens between the two ships. They come towards each other, they collide at that point there. We're going to assume that they're not going to keep moving on, but that's how they would move. And so we can also see that the ships are traveling along in a straight line. Let's just have a look at what happens when we include ship 3 in this equation. Now, ship 3 is traveling along this line here, and you can see the ship 3's line does cross with ships 1, but the question is, will they cross at the same time? So we'll just go and play the slider for a little bit, and you can see that definitely they're not going to cross because ship 3 is actually traveling in the opposite direction to ship 1. So at time 0, this is where ship 3 is, this is where ship 1 is. We can see that the two lines are diverging, so they're getting further and further apart, whereas they were converging up this end here. But they're definitely not going to collide because they're not going to pass the same point at the same time. Ship 3 would pass this point over here at some point in time, but it's long before ship A even gets there. Alright, so let's just look at one more example. Assume ship A is initially at position 3050 at 9 AM and is traveling with a velocity vector of 12 - 3 kilometers per hour. He has a position vector of 4830 at 9 AM with a velocity vector of 8 and 2 kilometers per hour. Will the two ships collide? What we need to determine first is what is the vector equation of the ship A and what's the vector equation of ship B. These are two different ships to the ones previously talked about. So the position vector of the line of ship A is going to be 3050 plus t. Let's just call this t1 for now. 12 and -3. And the position vector of B is going to be 48 and 30 plus t2 and 8 and 2. Now remember, for these two ships to collide, we're going to want that t1 is going to be the same as t2, And in this instance, they're leaving at the same time. So we do need to consider if we would have to move that forward or backwards if ship B did leave later than ship A. And again, what we want is we want the position vector of A to equal the position vector of B. So we want 30 plus 12t1 and 50 take away 3t1 be the same as 48 plus 8t2 and 30 plus 2b2. And again, what we can have is we'll set this up as a simultaneous equations comparing the x and the y values. So when we compare the x values, we have 30 plus 12t1 equaling 48 plus 8t2, and we have 50 take away 3t1 equaling 30 plus 2t2. And what I'm going to do is I'm just going to set that up in our ClassPad quickly. And again, we'll set up as a simultaneous equation. Again, I'm going to call my t1x my t2y. So 12x equals 48 plus y, and 50 take away 3x equals 30 plus 2y, and we're solving it for x and y. And again, we can see that make the standard form, it's 49 over 12, that's 31 over 8, so we end up with t1 equaling 49 over 12, and t2 is going to be 31 over 8. What we can see here is that the two paths will cross at t1 and t2, but since t1 does not equal t2, because they're different, the two ships will not collide. The two ships will not collide. And the reason they don't collide is because they cross the same point, but they cross at different times. Just like what we saw before, we saw that ship 1 and ship 3 crossed the same point. They would have crossed the same point, but they crossed at very different times. Whereas when you compared ship 1 and ship 2, they crossed the same point at exactly the same time. That was in the previous example. This brings up the next question. If they don't collide and they both leave at 9 AM, what time would ship B need to leave for them to collide? So the way we're going to approach this problem is we're going to use the same time parameter t, but we're going to delay ship B or make ship B leave a bit later on. So the position vector of A doesn't change. It's still going to be 30 and 50 plus, and we know that this one's going to leave a time t, and that's going to be 12 and -3. And ship B is still at 48 and 30 plus. Now we're going to delay ship B or extend ship B by some factor A, and that's still being multiplied by 8 2. So again, we want vector A equal second vector. What that looks like is 30 plus 12t and 50 take away 3t must be the same as 48 plus 8 t take away A, and we have 30 plus 2 t take away A. Again, we've got two variables, two unknowns, so we can solve this simultaneously. So the first equation is going to be 30 plus 12t equals 48 plus 8t minus A. The second equation that we need to solve is 50 take away 3t is going to equal 30 plus 2t take A, where A is the delay or the extension that we're going to give ship B. So again, what we're going to do is we're just going to put that back into the equation. So we're going to clear all variables, clear everything out of there, and we're going to type in these two equations. Now I'm going to call tx and I'm going to call a y. So what we've got is 30 plus 12x, 30 plus 12x, and that's going to equal 48 plus 8 bracket x take y. And the second equation is 50 take away 3x equals 30 plus 2x take y. And we're solving for x and y, where x is the t parameter and y is the a parameter there. When we solve that, we get 49 over 12 and 5 over 24. So they're going to collide at time 49 over 12. And a needs to be delayed by 5 over 24. So if it leaves 5 over 24 hours later, the two ships will collide at time 49 over 12. That's what that's saying there. So what time will ship B need to leave for them to collide? Well, it would need to leave at, and let's just convert this 5 over 24 into a decimal. So convert that to a decimal, 0.2, and we'll times that by 60, because that's that's in hours. It's converted to minutes. 12.5 minutes later. So ship B would need to leave 12.5 minutes after. I'll get rid of the calculator. We'll need to leave 12.5 minutes after 9 a.m. or 9:12 5 a.m. If it leaves just a little bit later, it will get there on time. Now let's just see how that 12.5 minutes compares to the previous answer, because we can see how we get the same t value of 49 over 12 as we had before. So before we had a t1 is 49 over 12 and t2 was 31 over 8. If I do 49 over 12 take away, so we'll get the fraction right now. If we do 49 over 12 take away the 31 over 8, that tells us how much longer B would have had to wait for it to collide with ship A, which is 5 over 24, which is exactly what we got for our A value there, 5 over 24. So if you haven't already worked out the T1 and the T2 values, and this is why I chose different T times there, the way you'd solve it is just by using the same parameter T, but delaying one of the ships by time A. So ship B would need to leave 12.5 minutes after 9 a.m. They would need to leave at 9:12.5 a.m. Last question. The position vectors of two particles are given as follows. So we've got position vector 1 at time 1, and we've got position vector 2 at time 2, and we want to do these two particles collide. So pause the video, have a go for yourself, see if you get it right, and then we'll go through the solution now. So I've got the position vector A is 4 plus T1, 20 minus T1, and we've got the position vector of particle B, which is 5 plus T2 and 4 plus 2T2. And we're looking for where RA equals RB. Now I'm not going to write that whole thing out again. I'm just going to compare the x components. So we want 4 plus T1 to equal 5 plus T2. That means that T1 is going to equal 1 plus T2. So that's for the x components. Now for the y components, 20 take away T1 equals 4 plus 2T2. And again, we're going to have T1 equaling 16 take away 2T2. These two T1s have to be the same if they collide. So we're going to end up with 1 plus T2 is going to be the same as 16 minus 2T2. We'll pull the T2s across, so 3T2 is 15. So T2 is going to be 5. That means that T1 is going to be 6. So do these particles collide? They don't actually collide though, do they? Because T1 does not equal T2. So T1 does not equal T2. So do these two particles collide? No. But do their paths cross over? Yes, they cross paths, but not at the same time. So therefore the particles do not collide, because they will cross the same point, but they'll cross it at different times.